Hello, everyone. Welcome to today's seminar. Today we have Rodrigo de Salvo Braz, who is a research scientist at Meta, formerly known as Facebook. He has worked since his PhD on symbolic probabilistic inference methods, including lifted inference and probabilistic inference modular theories, with a particular interest on probabilistic programming. He worked as a postdoc with Professor Stuart Russell at UC Berkeley on probabilistic programming language called BLOG, and then at SRI International Developing Symbolic Probabilistic Inference, and he led one team on a DARPA program on probabilistic programming for advanced machine learning program. And since 2021, he joined Meta as a member of the Beam Machine team. And I'm so glad to see you here, Rodrigo, and looking forward to the talk. Thank you.
Thanks, Gabriela. Thanks for inviting me, and thank you all for coming. Feel free to interrupt me. I don't have a ton of slides, so we should have enough even if people have during the presentation. So I'm going to talk to you about Beam Machine, which is which is our probabilistic programming system developed at Meta. The target audience is just people with computer science background, software engineers, and so on, who may not know very much about probabilistic inference and probabilistic programming. So I'm going to explain probabilistic programming in general, just to get the general idea, and then go into details about Beam Machine and what gives it a unique flavor. So what is Beam Machine? It's a probabilistic programming language and system, and its purpose to perform efficient and expressive Bayesian inference. And it's been created by the Bayesian modeling team at Meta. I will explain more about what all that means. Things to note is that it's built atop PyTorch, so it brings along the strengths of PyTorch. It supports a declarative modeling style. You declare the problem without having to worry too much about how to solve it. It's compositional, meaning you can combine different solutions together, and it enables novel inference methods to be developed. So Beam Machine is open source. It's being released as a beta version in last December, so it's pretty new in that regard. The website has a lot of documentation, has detailed tutorials, and you can very easily run the tutorials on your browser on Google Colab. So it's pretty convenient, and the tutorials are really meant for a general audience. So if you're curious, I definitely recommend going there and following the tutorials, and you're going to get a pretty good idea what this is about. So before we go into Beam Machine proper, I'm going to tell you about probabilistic programming, because that's also kind of new, not very mainstream. So most people probably are not familiar with the details. I'm going to start with a very simple example involving just flipping a coin, because that's pretty much the simplest possible probabilistic problem you can have. So in English, I would describe this problem as a coin that's being flipped multiple times. And this coin may or may not be fair. So there's a heads bias, which is just the probability of flipping heads. We don't know what the heads bias is. We have a prior belief, basically a guess. That corresponds to the probability of having seen the coin being flipped twice heads, twice tails. That doesn't mean it's fair. It could have been just a coincidence, right? And it's not a very strong probability belief, because just 4 flips. If I had flipped, 20 heads, 20 tails, it would be a much stronger belief that the coin is fair, but here it's not that strong. So that's the situation. And I'm curious to flip the coin further and estimate what the heads bias is. So in math, in statistics papers and so on, people describe this problem, something like this. Heads bias is a probability that is itself a random variable because I don't know what the probability is, I'm estimating it, and there is a distribution over that probability. And the prior distribution of that probability is beta 2,2. Beta 2,2 is just a mathematical way of saying what I said before. It gives a distribution over the probability of a coin that's being seen flipped twice, twice heads, twice tails. That's just what that is. And then I have a family of random variables. You see there's an index here, an index I, because there are multiple tosses. So they're coin toss 1, coin toss 2, and each of them follows a Bernoulli distribution, which is just the probability of being true or false with a given probability. So the probability here that I get heads is the heads bias, the probability. So I follow this Bernoulli distribution. So it's a pretty simple statistical model or generative model or a distribution simply. Okay, so in STAN, which is a probabilistic programming system that's been going on, that's been around for maybe more than 10 years now. It's very widely used. In STAN, a problem like that is defined something like this. As you can see, it follows the mathematical notation quite closely. The difference here is that you also specify the type of the variable, but it's pretty close to the mathematical form. And in Big Machine, we define it like this. Basically, we just use Python to define it. Each random variable or each family of random variables is going to be a Python function. And this Python function has to return the distribution of the variable. Here, heads bias is a family that has a single random variable, just heads bias, so it has no arguments. The other function, coin toss, has an argument I, which is the index. So for each call here, coin toss 1, coin toss 2, I'm going to have a different random variable. And this is the distribution that it's going to follow. Here, the Python function here is very simple. It's just returning a distribution object. It could be arbitrary Python code. I could have a lot more complicated description of the distribution. I could have if then else statements deciding which distribution to use depending, say, on the time of the day or something like that. So it's very flexible. You just use Python. Now, if I define a model like that, how do I use it? What's the context that I use it with? So the workflow, the typical workflow is that you define the model, then you bind the observations or the data. I'm going to give details soon of how this is done. And then you estimate what you're interested in here, heads bias. So basically going to flip the coin. Those are going to be my observations. And I want to know what's the probability of heads bias given that extra data. And then I'll process results, which I'll show what that means soon. So the model, I have already shown you that. Here, I just added a few more comments, basically saying the same things I said before. So you just write your model. That's the prior distribution. Before seeing any data, this is what you know about the problem. This is what you believe, how the structure of the problem is. Then we bind observations. In Big Machine, this is just a dictionary, a Python dictionary, mapping random variables to a value. So here 1 represents heads, 0 represents tails. So this is the first coin toss, the second coin toss, and so on. They are all different random variables. As you can see, the data here, I get heads 9 times and just tails 1 time. So, you know, looks like the coin may be biased, although that might have been just a coincidence. We don't know. And that's why the estimation of the heads bias is going to be just a probabilistic estimate, because we cannot really know for sure what the value is. In Big Machine, actually, this is going to be a PyTorch tensor. I didn't include it here just for simplicity, but we use PyTorch tensors to represent data, to represent values. Okay, so the next step is to estimate heads bias. The query could be another variable. Here we're choosing heads bias because that's the variable of interest. and given the observation, what's going to be. So in Beam Machine, we do that by selecting an inference method. So this is the name of one possible inference method. And then you infer, you tell it what are the variables in the query that you're interested in, the observations that you have, the number of samples that you want to generate, and the number of chains. Number of samples is because we are using a sampling method. Basically, it's going to generate many, many samples of the distribution of interest. So you can infer details about that. And it may do that in separate chains. You can sample 4 parallel chains of samples. This is going to be a little bit clear later in the presentation, but that's how it works. You just give this command, there's a statement, and then you get a set of samples that you can use to check things about your distribution. So the last step is to process those samples, those results. So one thing you can do with the samples is to plot. Here I'm plotting the probabilities had bias that I obtain given the observations, right? So this bar here is the mean of my prior belief, because I had a belief that corresponded to seeing 2 heads to tails. My prior belief was centered on the fairness, right, on 0.5 probability. That was prior. But after seeing the data, this green line here is the proportion of heads in the data, so 0.9, because it was 9 out of 10. And this is the posterior, the mean of the posterior heads bias, meaning this is the distribution. This curve is the distribution of heads bias. Because I saw so many heads in the data, most heads bias are going to be on the high end of the spectrum. But it could be as low as 0.4, for example. There's a small probability that it's actually biased towards tails, but I still saw a lot of heads in the data just by coincidence. But overall, the likelihood is that it's on the high end, and the mean of the posterior is 0.8. So it doesn't go as far as 0.9 like in the data, because our prior distribution, prior belief was on 0.5. So now we got swayed towards 0.9. We don't get all the way there. This is 0.8. So actually, this is a way of regularizing, if you're familiar with that term in machine learning, which is to say, you don't just go, you take the data completely at face value, you combine that with prior beliefs that you have about your variables as well, and you get something in the middle. Another thing you can do with the samples is to print diagnostics. I'm not explaining exactly what this is, but one thing is R hat, that's a measure of how good your estimation is. If it's close to 1.0, that means the estimation is good. You had enough samples. If this is greater than 1.0, you might have to generate more samples to get a better estimate. So Beam Machine gives you the tools to evaluate that as well. So that's how it works. That's the typical workflow of probabilistic programming in general, Beam Machine in particular. Now, I have been talking about probabilistic inference. That may be a little confusing, especially if you're coming from other sides of machine learning. So just a brief definition here, what I mean by that. Probabilistic inference. It means solving the following problem. Given a model that encodes a prior distribution, basically what you know already about the problem, and given a set of observations O, which is just assignments to a subset of the variables, here the coin tosses. I'm going to compute a posterior distribution of Q, where Q is a query. It's a subset of the random variables of interest. In our case, that was heads bias. And yeah, that's going to be a posterior distribution of Q given the observations O. Now, one thing that may be confusing to people who are using these terms in different contexts is that if Q, the query, are parameters of your model, meaning non-observable random variables that they define the model, but you don't get to observe them, like the heads bias. You don't observe them directly, you just observe them through coin tosses, for example. Then if you perform inference like I described here, what you're doing is learning. You're learning that parameter, right? You have data and you're learning the values or the probability distribution of unobserved parameters of the model. Now, if Q is other variables, for example, the 11th coin toss, right, which we haven't seen yet, but we may want to estimate or predict, then inference is going to correspond to prediction. I have data that's going to give me an idea about the parameter, and that may allow me to make predictions about future behavior. So that's what I mean by probabilistic inference. Now, in machine learning, how does that connect exactly with machine learning? In machine learning, usually you define some kind of model and you observe, you estimate non-observed variables based on observed data. And then you may use the learned parameters for future predictions. So that's the typical machine learning workflow, and that's how probabilistic programming supports it. Now, I talked about the clarity. Any questions so far? Because now I'm changing sections. Just, yeah, let me know if you have any questions. But I mentioned declarative modeling. What does that mean? That's not so usual in machine learning. Usually we use discriminative learning. So what do we mean by that? So Beam machine and probabilistic programming, they usually, you only need to describe the model. What is the model? The model is code, it's knowledge about your domain, about the structure of your domain. You don't need to write code to solve the problem. That's separate from the code that solves the problem, right? The code that solves the problem, which we call the inference engine, is the code that actually generates the sample, that computes the diagnostics, that computes the posterior distribution. The user of the system doesn't need to write any of that. The only code that they write describes their application domain. The inference engine is provided as part of Big Machine. In the case, of course, of other probabilistic programming systems also, it comes with one or even multiple inference engines. So the user only needs to encode the model of their application domain, which is what they know best. So that's a good division of labor there. I like to make an analogy with constraint programming, right? Because in constraint programming, you define the constraints of your problem. Here I have two variables, X and Y, and I'm just saying, well, I want to find a value of X and a value for Y such that X is greater than or equal to 2 times Y plus 3. So I wrote this, you can think of this as code, but this is not code for solving the problem. It's just defining the problem. And a specialized solver written by experts may come and read these constraints and generate a solution for you. And with Big Machine or probabilistic programming, that's the same thing. You can think of your model as a set of constraints. Here I am relating coin toss, the family of random variables coin toss, to heads bias. There is a certain relation that I'm defining that has to be respected when a solution is provided. The observations themselves, I'm not including them here, but the observations when I observe data, you can think of that as constraints as well, right? Because I am constraining my posterior distribution to be something that generated that data. And again, an inference engine takes the model that you wrote, which here is code, Python code, and finds a solution, which is the posterior distribution. Declarative modeling is useful for two things: for usability, because the syntax is more intuitive. So it's easier. When you write the model, it's almost like writing a story, right? I'm going to have a heads bias, and I'm going to toss the coin. You just write this kind of causal sequence of events relating one to the next. And it's like telling a story, how the data is generated. And that's easy to do. It's much easier than trying to write the code to solve the problem. You just need to declare it's one distribution per variable, and you're done. In terms of performance, that also helps, because when you write a distribution per variable, you're writing a decomposed form of the model that the inference engine can use to leverage and do a better job in terms of performance. All right, so how does inference actually happen in probabilistic programming? Here's a naive way to do that, right? It's not really how you want to do it because it's not efficient, but it gives you an idea how you could do it if you had to. So you have the model there. One way to do that, you just run the model because the model is a Python program. You could run it and generate this data, multiple executions, thousands of executions of your model, and just collect the data, right? So first time you run it, heads bias is sampled from the beta distribution, is 0.53. Then you generate 10 coin tosses, and this is what you get. And a second execution, 0.41, same thing. Here, you get a pretty extreme heads bias, 0.89. There's a lot of heads, coin tosses, and so on. Now, these are samples from the prior distribution, right? They didn't take the data into account, just the model. So it reflects how you believe things are before you see any data. Now, when you do take the data into account, one thing you can do, you can go to those samples and just throw away all the samples that do not conform with the data. So here, we do have two rows that agree with the data. So I can just select those and throw everything else. And if I do that thousands of times, the samples that I keep are going to be extracted from the distribution that would be defined by this data because I use this data to select that. So now I would have 1,000 samples or many thousands of samples of the posterior distribution, and I can go look at the heads bias that I got, the mean or the distribution. I can plot the graph and so on. And that's a very intuitive way to do that. It's kind of simple to even implement, but of course not efficient because you're throwing away all the samples. You have all the trouble of generating the samples and then you're throwing them away. And that's wasteful. So there are better ways of doing that. And I'm not going to go into all the details, but I'm going to give you an idea how this inference, more efficient inference works. And for that, we'll need a bigger example. So the example that we have now, I have the time of the day, which is just a uniform distribution between 0 and 24 hours. Then I have a sprinkler on my lawn, and that's going to be on or off. And when the time of the day is between 10 and 12 p.m., it's very likely that the sprinkler is going to be on. Otherwise, it's very unlikely that's going to be on. It's just probability 0.01. But in that particular time range, it's high, 0.95. There's a probability that it rains, and it's relatively low, just 0.2. And then there's a probability that the grass in my lawn is wet. And that's actually, I cannot read what I wrote here because, yeah.
We can
I
see
think
it.
it's saying that, yeah, I cannot see it because Zoom is covering it, but that's
one
okay.
If sprinkler or rain, else 0, 1.
There you go. So if it either the sprinkler is on or rain, then the grass is wet with probability 1. Otherwise, it's unlikely that's going to be wet. My observation is that the grass is wet. So I walk out and I see that the grass is wet. And I want to know what's the probability that it's because it rained or because the sprinkler was on. And that's the model in graphical form. It's just a Bayesian network for those who are familiar with them. And here I have a value 1 to grass is wet because I observed that. So that's the model. Now we're going to use Markov chain Monte Carlo, which is a inference method for doing that. And the nice thing about this method is that it takes the data into account all along, right? Unlike the rejection sampling that I showed before that generates samples and then throws them away given the data, here I use the data to generate the sample. That's why it's going to be better. So I start with some initial sample here, just some random values here for all the variables. Sprinkler is on, rain is off, it's 11 a.m., and the grass is wet. So the next step is to say, oops, let's see. So I choose a subset of variables. Here I'm going to choose just one variable, rain. Not because it's the query, it could have been any variable. So I chose rain. I'm going to choose any one that are not observed, because the observed are fixed. I just leave them alone. I pick the ones that are not fixed, and I propose a new value for them. So rain was 0. What about if it were 1? So now we analyze that. That's a pretty likely configuration because the sprinkler is on, but it could have rained as well. There's a probability 0.2 that it rained, so it's fairly likely. So we accept that. Okay, that's a good sample. So now we have a different situation in which it had rained. Okay, so we accept that. So we generate that sample. Now we do the same thing from the current sample, right? So that we form a chain of samples, and that's why we call this a Markov chain. And we generate a new one. So now I'm going to select sprinkler. I'm going to propose a new value for it. And I'm going to see how likely it is if I'm going to accept that or not. Now, that's not so likely, right? Because when time is between 10 and 12, it's very likely that sprinkler is on. And here it's off. So not very likely. So we will probably reject that sample, even though sometimes we will accept it because even rare events may happen sometimes. So we need to sample from them as well. But typically we will reject that because it's so unlikely. And we'll do that in a way that's smart. And I'm not going to get into the math of it, but there's a kind of sophisticated rule for accepting samples such that they reflect the posterior distribution, which is what we want. Here, I am showing an example of single site MCMC, meaning I'm just switching one variable at a time. But in principle, I could select a subset of the variables or even all of the variables at once, the ones that are not observed. In general, you could do that. Here, we're doing just single site. Okay. So that's how MCMC sampling works. That's the main method for probabilistic programming systems, not just Big Machine. There are other methods. There's, for example, variational methods, and there are even symbolic methods. But that's the main one, and it's very efficient, and it's very applicable. It's very generic because it applies to pretty powerful languages. So it's a nice inference method to support. So now let's take a look at Big Machine highlights. What is more unique to Big Machine? What gives it its unique flavor? So one thing is that Python is accessible. So it's just Python. A lot of people already know Python. You can write your model using a language that you already know. So that's a very nice thing. As far as I know, it's pretty unique to Big Machine. There's PyMC, which you kind of write things in Python, but it's not exactly the model. It's more like you build a graph. It's a little more indirect. So that's a nice feature of Big Machine. And it's universal. You can use arbitrary Python code inside your functions, returning a distribution. So that's pretty nice. And it uses PyTorch, and that means we have the strengths of PyTorch available, like autograd, GPU support, and things like that. The inferencing Big Machine is pretty customizable and flexible. We have multiple inference methods, and they can be combined to some extent. You can use one method for one part of your model, another method for another. I'll show you more details of that soon. So it's nice that it's customizable like that. And it's performant because even though on Python itself, we do have a Python inference engine and a C++ inference engine. The Python inference engine is universal and it's very flexible, but it's not as performant because it's an interpreted language. But the inference engine in C++ is very fast. It compares with Stan. Stan is also very fast, but it's been around for many years now with a very large development team. So Stan is fast, but our C++ layer is very competitive with Stan while supporting other things that Big Machine supports. So that's a nice thing about the C++ layer. So one of type of inference that we support is single-site inference, which is the kind of example that I gave you before, showing switching just one variable at a time. One advantage of that is because you're not changing the whole sample at a time. So that gives you a greater chance of getting your samples accepted. The more samples that are accepted, the more performance you have, right? Because you're generating the final set of samples that are accepted. You're generating more of those, so you're going to have more accurate estimates and so on. Even inside single-site inference, we have multiple ways of doing that. There's ancestral sampling, which is kind of the basic one. There's Hamiltonian Monte Carlo, which originated with Stan, but we also support that. Both HMC and NUTS, which are very advanced MCMC inference methods. And we have an in-house developed Newtonian Monte Carlo method, which is, I believe it only been machine supported so far, and it's pretty efficient, and we use it even in production problems that matter. So the way Newtonian Monte Carlo works is you define our model. If that model is differentiable, then we can compute the first and second order derivatives of it and use those derivatives to approximate a Gaussian around the distribution and get proposals for the values inside MCMC from that Gaussian. Sampling from a Gaussian is very easy, very simple, and very efficient. So that's one way to generate good proposals very fast. And that's basically how this method works. There's compositional inference. This has to do with using different methods for different variables. So in Beam Machine, you specify it this way. You use the compositional inference method. And you say, well, for the family of variables heads bias, which is a family with a single variable, I'm going to use Newtonian Monte Carlo. Newtonian Monte Carlo only applies to real valued variables, continuous variables, which is the case of heads bias because it's a probability. So we use it there, but we cannot use it for coin tosses because coin tosses are binary discrete variables, it's either 1 or 0. So we cannot just apply Newtonian Monte Carlo to that. So we compose that with ancestral metropolis Hastings, which is applicable to that. And in this way, we managed to do inference on the entire method, on the entire model, combining different methods. And of course, that's useful because you can then apply methods that are restricted to certain types of variables. And you apply that to just those variables and you use other things for other variables. You can mix and match. Another type of inference that Beam Machine provides is block inference. So going back to our example, I mentioned that this was problematic to have sprinkler 1 because the sprinkler 0 when it's 11 a.m. in the morning is unlikely. So it's not going to be accepted. So if we have a configuration like that, how do we move away from it? How do we get sprinkler to be 0 at some point? Because we do want to generate samples with that value as well. And so, well, no problem, because at some point we're going to select time and then we're going to change the time. But the problem is that if we select another value for time that's out of my range here from 10 to 12, say 9, now this is also unlikely because out of the interval from 10 to 11 to 12, sprinkler is usually off and here it's on. So again, this is unlikely. So again, it's probable that we're going to reject the sample as well. So we kind of get stuck in this pattern in which the sprinkler is on and we are between 10 and 12. And it's hard to move away from that, but you do want to move away from it because you want to sample from scenarios in which it's not that time of the day. And the way to do that, one way to deal with that situation is to do block inference in which you now propose a value for the joint tuple of those variables. I select both of them and I select a new assignment to both of them. And if I do that, at some point, I'm going to propose a value like 0 and 9, for example. And that's also a likely configuration because at 9 a.m., sprinkler may be 0. Yes, Gabriela.
So can you do this for more and more variables and block across multiple variables? Because models can be very complex at one point, right? And yeah, the space can grow significantly.
Yes, what happens here is that usually it requires the user to have an idea which variables are going to be highly correlated and then inform the inference engine. You know, these two here, they should go together. And the way you do that in Beam Machine is by writing something like this. So here we're using the same method for all these variables, but sprinkler and time are specified in a single tuple here. And that tells the inference engine that they should be sampled together. Yes, you could generate all the combinations. Typically, you don't want to do that because you just want to indicate what are the problematic tuples. Right here, we still leave grass is wet and rain alone, and we just couple those two. But you could generate many different tuples here. It wouldn't be particularly problematic. It would just be a slightly longer specification. You're not going to do all the combinations. It's not going to be like the exponential number of combinations. Yeah, so that's one way to do that, and it's pretty easy to specify it like that. All right, so those are the types of inference that Beam Machine supports. Another one is what we call Beam Machine Graph. This is the C++ inference engine that I mentioned. It's very easy to use from the Python level. You just write your model in Python as usual, but now you're going to use this method called BMG inference. And everything else is the same. You can replace just that little bit to try the C++ inference engine. And what happens is that a compiler that was developed by our team is going to take the Python model and it's going to represent it as a C++ data structure that the C++ inference engine uses. Now, there's a catch, which is this compiler, because, the Python models, Python is a universal language. You could use arbitrary Python code there. And the C++ inference engine data structure only represents a subset of possible models, a restricted class. So it's not going to work for every single model that you write. But when you write a model that happens to be supported, then it's going to have much greater performance. And the good news is that this restricted class, even though it's restricted, is still very widely useful. Basically, for example, any Bayesian network fits this class. So if you write something that's equivalent to a Bayesian network, it will work. And some things that are not Bayesian networks will also be part of the class. So it's pretty generous still, and it's much, much faster than the other inference engines. So, and, it's nice to try. If you write your model, you try this. If it compiles, great. If it doesn't, then you can use the Python model. So I told you about inference methods that are based on sampling. Sampling, it's a little, this is early days for probabilistic inference, probabilistic programming. Sampling is kind of the first thing you try, right? Because it's almost like a poor man's approach to inference, because it's almost like brute force. You're just simulating the model and generating samples, right? You're not reasoning about the model in a way that a statistician or a mathematician would. And one example here, in the heads bias problem, we had a prior belief on heads bias, which was beta 2.2, which meant as if I had seen two tails and two heads so far. Then I observe 9 heads and 1 tail. If you know statistics, you know probabilistic methods, you immediately know that the exact solution for the posterior distribution is beta 11.3, because beta 11.3 is the probability that you get when you observe 11 heads and 3 tails. So if you just get the prior and you add what you saw in the data, you're going to obtain this posterior. So generating 10,000 samples is unnecessary, really, because you could immediately and in constant time generate the exact solution. The samples are not the exact solution, right? Because when you sample, there's always going to be some error there related to sampling. It's not, you're not going to get the exact answer. You're going to get an approximation. You're going to plot and you're going to get something that fits the curve, but not exactly. Whereas you could have just gotten the exact analytical answer. So why don't we do that? We should, and we will do that. And other research teams are working on similar thing, which is analyzing the model. You get the Python model and say, oh, there's a static analysis that you can do. Say here, I don't need to simulate this part here. I don't need to sample. I can just replace it symbolically by the exact answer. And it's going to be much faster. Another good example, when I observed the data, I don't know if you remember, but the 6th coin toss was tails. All the others were one. And we then filter the data in terms of we filtered the samples in terms of the data. We threw everything that was not the 6 coin toss equals 0 and everybody else equals 1. We threw everything out. Now there's a symmetry, right? Because it doesn't matter at all that it was the 6th coin toss that was 0. If it were the 5th or the 4th, the data would be just as representative. So we didn't have to throw away the data that had one tail but was not the right position, because there's a symmetry. Now the inference engine, the naive inference engine, doesn't know that, so it uses that information even though it doesn't have to. Again, by reasoning symbolically, by analyzing the model, you can see, well, there's a symmetry there. It doesn't matter which toss was tails, which one was heads. I just care about the number of tails and the number of heads. So I can simplify my model and aggregate all those cases that have the same histogram, the same count, and do a much better job. So again, that's a kind of static analysis of the model that symbolic inference does. And so this is something that we're working on to make use of that. And that can be mixed with sampling, right? It doesn't have to be one or the other. You solve what you can with symbolic inference and you sample the rest, what's not amenable to symbolic inference, and you get a resulting combination that's better. So that's one direction that we're going. And I think that's pretty unique to Beam Machine. It's not something that I see other probabilistic programming systems investing on very much. Another one, there's a whole line of work on compiling PyTorch models, right? Because PyTorch, there's still some overhead. Even though PyTorch is implemented at the C++ level, there's some overhead, and there are compilers that make it even more efficient. And because Beam Machine is based on PyTorch, we can benefit from that as well. And we're working on that. Then there is things like causal inference support. So for those of you who are familiar due to Pearl's work on causal inference, you have an operator called the intervention operator, which is when you actually set an observation to as an intervention, not as an observation without intervention, that helps you defining and identifying causes in your model. And that requires an extra level of notation that we're working on to incorporate to the language as well. And that's it for the system, the description, what we're doing, what we are going to do. I just wanted to tell you a bit more about the team and what the kinds of tools that we are working on. So we have a part of the team that works on infrastructure. That's basically what I told you. The inference engine, the C++ layer, the compiler, and so on. We also have a tool which is called PPL Bench. That's for benchmarking probabilistic programming systems. That's also open source. And it benchmarks not only Beam Machine, but Stan and other models, other systems for comparisons. And we have a whole part of the team that's for collaboration with other teams at Meta for using the system in real problems that the company faces. So I'm going to tell you a little bit about those applications for you to get an idea how this can be useful in practice. So, of course, Meta and any other social media company has to watch for content violations of ads and also user-generated content. to see if it's not violating some kind of policy. And that's a very costly thing to do because it requires humans to look at the content one by one and flagging that and checking if it's really violating or not. So we have a system that helps with that, basically by observing how the human labors label content and assigning a probability of whether that's really violating the content. Because of course there's noise when you have human labelers. They may make mistakes or they may have different opinions. So there's a need for some probabilistic reasoning on top of that to decide whether something is really violating. And if you don't do a kind of more sophisticated analysis, then what you have to do, you have to use even more human labelers, and that's a very costly operation. So by using this probabilistic inference on top of that, you're able to flag content violation with the same confidence, but with less human labeling. So it helps the process and helps making it more efficient. Another aspect of this work is that you can even learn the characteristics of different human labelers. You can, for example, estimate how reliable each human labeler is so that you can do an even better job at deciding whether you have a confident decision already on the content or whether you need to require more human labeler using this kind of collaborative analysis of the labeling. Yes.
When you say the human in general, or are you looking at individual users? So are you building also some sort of confidence level in the users who are labeling things?
No, these are, when I say human labelers, I'm referring to Meta employees that are hired to check the reports, not the users of the product, like external users.
Got it. I misread that part. Thanks.
Yeah. So it's basically checking the confidence that we have on each of the employee human labelers. Yes. And another aspect of the work, I'm sure many of you heard of things like A/B tests. When you have a new feature and you have something with billions of users like Facebook or Instagram, you need to test that before releasing that completely. So what you do, you release that feature to a subgroup of the users and you see if the response is better, if that feature is actually helping your metrics. Now that calls for a decision there, like how many users are going to see the new feature? After how long are you going to decide whether that's being useful or not? And even if it's useful, it could have been just noise, right? Maybe it was useful because just by chance. So you need a hypothesis testing there to decide, oh, this is actually reliable. I do have a reliable indication that this is a better feature than what I had before. And those are not things that humans are naturally, it's not naturally easy for humans to make those decisions because you need to kind of do the statistic calculation to decide what is the size of the test group that you need and so on. So this model here predicts the required sample size that you need to make confidence decisions. In fact, before the system, we found out that a lot of ABT tests at the company, we thought that they were being very informative when they were not. So by doing that, we have a greater confidence that the features really are more useful than the previous version. And another thing that we do related to experimentation is that you have multiple metrics, right? You can measure how good a feature is based on different metrics. Now, one thing you can do, or the developer of the feature can do, is to define many metrics to see which ones improve or not. But the problem with that is that if you add too many metrics, you're kind of throwing everything and seeing whether it's what sticks or not. Then it starts becoming meaningless, right? Because you have so many metrics that you have noise, and some things may be noise, some not. So what the system helps doing is using probabilistic programming to identify which metrics are actually more useful so that you have a better estimation. So those are few applications that we work on using Bing Machine inside Meta. And of course, it's open source, it's out there, and we're just for a couple of months now, we're looking forward to seeing what people outside Meta do with it. So this is what I had. If you guys have any questions, I'll be glad to answer. So thank you very much. Yeah, I see Mark Goldberg.
Hi there. This is a question coming from a complete amateur to your field. But one of the things that people do is they weight the more recent observations much more than distant ones. And that could be valid if you're looking at the weather or just about anything. There can be some drift in what's true. Does your model take into account that the probability of something may change over time?
No, I would say that's something that's part of the domain, the application domain, right? This is knowledge that you have as a user. Say if you're modeling something that depends on time, you have an intuition or from experience that distant observations will be less reliable. So what you do is that you put that in your model. You specify, you know, there's some noise, things drift, and you can actually encode that in your model. Say, I have a parameter here, but it changes every day, and that's how it depends on the previous value. If you create that knowledge and if you encode that knowledge that things drift, then naturally the inference engine will take distant observations less strongly than it does with the recent ones.
Thank you.
So that's not built in, because I guess in some applications, I guess it might be the case that distant observations are just as good. So you need to tell the system. Thank you.
So Rodrigo, thanks for the great talk. I had a question about your inference. You made in your future directions, you said that you would want to go with the symbolic approaches. I'm guessing that is because currently you're doing more approximate inference, right? So there are other kinds of other models, I guess, or algorithms that help in this exact inference also. What is your take on the complexity? In general, inference is computationally expensive with this, right? Approach.
Yeah,
so
very
what's
expensive.
the difference or scale at which it varies from approximate inference to this exact inference?
Or for any realistic applications, we're always going to need some kind of approximate inference, because the exact inference, but for the simplest toy problems, things just, yeah, it's completely intractable, right? Inference is really expensive. Even deterministic inference is already intractable, let alone probabilistic inference, which is even more uncertain. So, you know, this is like NP-sharp class of problems. It's really expensive. So there's always going to need some kind of approximation. What you can do is that if you have relatively cheap pieces of it that you can apply exact inference just to simplify the model, then you do that and you go with approximate afterwards. But yeah, it's a complicated problem. Even like deciding how much exact inference to do, it's not an easy problem, right? So
yeah. I think
it's
that's
kind of an empirical problem.
Yeah.
Sorry?
Yeah, I mean, what you suggested, like, you know, using a combination of both seems very interesting. Like,
yeah,
that might reduce the burden. The other question was, I think you kind of covered it in your applications, but what happens in cases where there is incomplete data? How well this model is faring?
So usually the data is incomplete. Go ahead.
Yeah, so I guess maybe, yeah, usually it is incomplete. So maybe when you have like imbalanced data or when you have lesser samples of a certain class, so how does this fare?
So if you have imbalance, for example, that's a good question, because that's when Bayesian inference becomes useful because you can encode your prior knowledge about your even your observation method, right? So if if you have imbalanced data, in a way, that's part of the model. It's because when a particular data sample is of a certain class, the probability of it being observed is higher. So if you encode that in your model, now your model knows that. It has that knowledge about the imbalance. And it's going to take that into account naturally, because that's just part of the problem. So this is a great way to naturally and in a very principled manner take care of that. With discriminative machine learning models, usually when you have imbalance, you have to do like kind of more hackish things in which, you replicate data artificially just to compensate. And, you hope that that's going to be the right thing to do, but you don't really know. Here, if you define the model and you put in that it's imbalanced and how it's imbalanced, now it's going to be a principle that's way of defining that's correct, and the model is going to use that. So to answer the question, the short answer is you encode that in your model, that the data is imbalanced, and there are ways of encoding that.
Thank you.
Yeah, sure.
I had a question as well.
Mm-hmm.
Actually, they're kind of tied to both the previous questions that were asked. So I work primarily in reinforcement learning, where the data comes in, and it's online reinforcement learning. So a lot of the data comes in as we are training. And the framework that you suggested is really beneficial in generating some of the samples, especially analytically generating samples which are useful. As well as identifying which metrics are really important at the last part where you said the HME, I think. So it would be really useful. But my question is, so as he's previously said that the distribution tends to change when you're receiving online, when you're doing online learning, the distribution tends to shift, but also the Markov chain also tends to grow, or sometimes you add new states. How does this, how would you support that in this framework? Can you increase the size of the chain as new samples are coming in?
Not sure what you mean by increasing the size of the chain, because the way I see it, you're generating samples and that's forming a chain. So as long as you're sampling, you always increasing the chain. So I wonder if you mean something different from that.
So initially, supposing I had the same sprinkler system with the time and the rain, right? So I have this and I'm making that query and it'll generate samples and I'm training, but then maybe 100, 200, 1,000 samples in, there's a new condition which it has never seen before, a new condition where there's now a third factor like a storm that also affects this thing. So now I have to change the chain, which we didn't know existed before. Can I program that in? Can I add that as a dynamic query?
Do you mean that's a new variable?
Yes.
A new type of feature? I would say the answer to that has to be the same answer that you have when you use, say, a neural network in reinforcement learning, right? Because if you have a neural network, you're going to have a fixed number of input variables. And if you have a new variable, I guess what you have to do is that you have to use embeddings or something like that to being able to encode different combinations. Here, you could probably do the same thing. You could define a set of variables that are going to encode.
Unknown. Okay, I see.
Like an embedded encoded. Yeah, it's not very natural in probabilistic programming to do that, just because probabilistic programming, you define the knowledge in advance and you're just estimating the parameters. So in a way, the knowledge is more fixed.
Okay.
But it's fixed in the same way that a neural network architecture is fixed, right? That doesn't mean that a neural network cannot deal with new things. And same thing with the probabilistic program. You can encode ways to learn. You can have like a,
okay, I see.
For example, an integer valued variable
treated like a new node. Okay, I see.
Yeah. Or you can have, say, a class there. Say you have a variable there that's just one variable, but it's an integer variable that has an unlimited number of values. And when you get a new case, you're going to explore a new value for that variable that variable never had before.
I see. And that wouldn't skew the process.
An unlimited number of cases. Well, you would have to deal with that. It's the same thing when you have like a latent Dirichlet allocation problem or a Chinese restaurant kind of situation, which you may have to grow your model as you go, like a non-parametric kind of model. So
Okay.
You may skew your process in the same way as you skew them in those other situations. It's not, it's basically the same problem and same answer in both cases.
Okay. Well, thank you so much.
Sure, thank you.
I think, Gabriella, that ends the questions from the students and researchers.
Yes. And I would like to thank again Rodrigo. And yeah, I'm hoping if whenever we hear students using the tool, we will send you the feedback if you want.
That would be great.
Yeah.
You know, I prepared this talk as a kind of, I hope to give similar talks in other places and kind of spread the word. So you guys were the ground zero for that.
Oh, okay.
Yes. So thank you very much for giving me this opportunity and for the great questions, and hope to hear back from you on that regard.
Excellent. Yes, sure. Thank you so much. And we'll stay in touch. Thank you.
Thank you.
you.
Bye.
Have a good weekend. Bye.
You too.